And so each farmer is playing this game of, is my field going to survive this incoming storm?
Why would I want this device in my field?
Farmers literally go out and push on the stalks.
All right, welcome to another episode of the BYU Tech Transfer Podcast. Today we have Dr. Doug Cook. He's a researcher here at BYU focusing on ag tech. And we have James Monson. He's a prototyping student in the Tech Transfer office, so we're excited to have them here. So without further ado, we'll jump right into it. So Dr. Cook, we're talking about two pieces of technology that were developed in your lab, the Rodney and then the gripper here, which we can see on the table. But Dr. Cook, why don't you give us maybe a brief introduction to yourself, the research that you're doing, the devices that we're talking about, and what they do?
Yeah, that's a lot to deal with. But so I did a PhD in human biomechanics. After I did a PhD in human biomechanics, I actually switched into plant biomechanics. And so I've been working in the ag space for the last 10 or 12 years. My research focuses on using engineering principles to try to understand how we can make plants stronger. The farmers have a problem with plants falling down. They always want as much yield as they can get. So you're pushing the payload up, but you don't want the thing to fall down. And the biologists are good at pushing the payload up, not so good at helping give the structural support that you need to keep that payload from falling over.
Right. And if I were to translate that into, maybe a little bit simpler terms, it means, corn stalks specifically, we're able to grow more corn, but it can't support the weight of all the corn that's growing.
Yep.
Okay.
Yep. So one of the things we've found is that if you think is a term called flexural stiffness, which is if you bend a rod like a wooden dowel, its resistance to bending is its flexural stiffness.
Right.
And what we found is that for corn stalks, that flexural stiffness is closely related to the strength of the stalk. So we've developed a device that goes out and kind of uses the same principle. You remember when you were a kid and you put one of those playing cards in the spokes of your bike and it goes rat-tat-tat-tat-tat-tat?
Yes.
Same kind of idea. We go out in the field and we push against the stalks with our Rodney device gently, and it pushes each stalk to the side gently as we drive through the field, and that flex that we push on the stalk, our rod is instrumented, the Rodney is instrumented, and so it can detect the force and the displacement that we imposed on the stalk, and from there we can calculate flexural stiffness. Flexural stiffness then gives us an estimate of strength.
Okay. And it sounds like there's a physical component to the device, right? The actual rod, and then how you're moving that through the cornfield.
Yeah.
And then a software component that takes the data that comes in from the physical device and then translates that into meaningful data for the farmer.
Yeah.
Okay.
It's fairly complicated to get the raw data into meaningful data.
Right. Yes. And so that's part of your research and what you've been focusing on. Great. So what kind of applications for this technology do you see in the agricultural space? I mean, we've touched on it a little bit, but specifically, I'm a farmer maybe. Why would I want this device in my field?
So for farmers in particular, they want, the vast majority of the grain that's grown in the U.S. is for cattle feed or I guess livestock feed. And so the plant grows and it's going to stand out there in the field until it dries down. And they want the moisture down as low as they can get it because then they don't have to pay to have it dried. And once it's dried, it's good for long-term storage. The problem comes that the longer it stays out in the field, the weaker the stalk gets. Because the plant it's no longer green and vibrant. It's this dry husk of a thing. And at the same time, you get these wind and rainstorms that come in. And so each farmer is playing this game of, is my field going to survive this incoming storm? And if they think their stalks aren't strong enough, they'll harvest to beat the storm, maybe, if a really big storm's coming. And then what they may have to do is they may have to pay to have the grain dried down. So that's an added expense. The idea with this Rodney device is you could go out and the farmers could actually get some quantifiable data on the strength of their stalks. And if you get good strength data back, you'd say, I think I'm gonna survive this storm. If you go out and you get poor strength, then you'd say, oh yeah, this is looking sketchy.
Right.
I'm gonna go ahead and it's worth it for me to pay the extra drying because it doesn't look. So it's essentially a risk analysis tool. Right. It doesn't look like I'm gonna make it, or it does. But now they've got some quantifiable information to base their risk analysis on instead of just kind of gut feel.
Right. And that's what I was thinking when you're talking. I was like, if I were a farmer, I can go out and I can guess, right? Based off of maybe, years of experience. Yep. Or I can go out and run a few tests with the Rodney, and I can know what is the strength of this, what's the size of the storm coming in, what am I expecting, and then I can make an informed decision instead of just a hopeful, I really hope that it doesn't get blown over.
And it's interesting you say the farmer, based on my years of experience, the farmers literally go out and push on the stalks. Yes. Literally, they say, and they feel it, and they say, how does it feel?
Yeah. And I don't want to knock the intuition of farmers.
No, they're pretty good.
Yes.
It's just that, we can calibrate this and, make it, and then you can interrogate much more of the field. Right. You can't go with your hands and do a whole lot.
I'm thinking specifically for breeders, right?
Okay, so that's the other application.
Okay, yeah.
The other application is the big seed companies, they want to run a breeding program, and they want to be able to say, here's a variety that has really strong, what they call stock quality, where they have a product that is going to have reliably a good strength to it.
Yes.
And they currently don't have anything that can quantify what they call stock quality. It's a very nebulous term. Each company handles it differently. Any company, I think, that can quantify that and put some data behind it has got an advantage.
Right. So instead of having a quality-based metric, right, you actually have a quantifiable-based metric where you could write the strength or the projected strength of the corn stalks on the bag of seed, so that you could then compare, here's my yield, here's my stock strength, this is my climate and the storms that we had over the past 10 years, and again, make informed decisions on what's going to give me the most bang for my buck.
And that can happen both at the end of their breeding program to quantify, or it can happen within their breeding program to say, make decisions about what to cull from the breeding program.
Yes.
This is a non-destructive test, so it doesn't hurt anything.
Right. So you could run this over and over and over again and get the data that you need to make those decisions. Now, I did have a question about that. When I was first learning about the technology, I thought the Rodney coupled with the gripper mechanism that we have here, and maybe we can talk a little bit about this as well, would be really helpful to farmers as the corn is growing to maybe make some sort of intervention into what's going on with the crops. Maybe they have some sort of beetle infestation or some sort of disease, or maybe they have, a water pipe that's busted and it's affecting, the strength of the corn. Maybe that's just me thinking. What are your thoughts? Could that be used?
Yeah. If you were going out and maybe laying down fertilizer on young plants and you wanted to see how things are going, and we made a miniature version of our Rodney, you could put that on the tractor and go through and take measurements. There's a lot of work on precision agriculture, which is the idea of mapping out your field and finding that there's some areas of the field that have poor soil quality. And so then you put down the nitrogen in an as-needed basis.
Gotcha.
Instead of just like blanket the whole field.
Right, because if certain areas don't need the nitrogen, right, you could save a little bit of money and put it where it's actually needed. Okay, so do you mind talking conceptually about what this device here is and maybe how it differs technically from the Rodney?
Sure. So this is a completely different product. This was developed, there was a company, Corteva Agriscience, put out a call for proposals for a way to assess stock quality, similar kind of metric, I think they said non-destructively and non-contact.
Okay.
So we took the concept of the same thing you use with your wall
stud finder.
Stud finder. There you go. Thanks. I couldn't think of the word. Your stud finder technology, and worked with Brian Mazzeo in electrical engineering, and that's the same concept we have here. You would slide this thing up the stalk, and you get some idea as you move up the stalk of the stock quality. So if you have stock rot happens within the stock, you would be able to pick that up. If you have pests, they will chew up the insides. The corn borer will chew up the insides, and so you could detect that. This would be more for the scientist kind of market. Okay. The breeder programs where currently they go out and they cut these. They do their test plots, but they cut each stalk in half with a machete. That's not very safe. And then
it's destructive.
It's destructive. Right. It's destructive. It's not safe. And then they lay them open. They have to by eye score each plant, and so they were looking for
a qualitative measure, right?
Yep. You're back to
subjective, depending on who's grading and how they're feeling that day, and all those good things.
So that was the idea. Here is you just run this thing up the stalk and use that kind of stud finder technology, and you get kind of a map of the stock quality of the stock.
Okay. And personally, I really love the idea of using them together, right? Where you have the Rodney, where if you could make it day-to-day use, right, you're getting data about your field and where you're having issues. And then if you're having issues, you could come out with a device like this and interrogate, individual stalks of corn and say, okay, like, is it a corn borer situation, or is it stalk rot, or what might be the problem, so that I can intervene and address this at the source.
Yeah,
And
you're
so
right. The Rodney is kind of designed to be field level.
Yes.
Where you can go through a lot of material quickly, and this is more spot checking.
Okay, nice. And then James, you were involved with kind of the development. I know we had a couple different interns working on it. You maybe weren't as involved as some of the others, but kind of peripherally what's going on with this device. So what do you think would be relevant? If I were an entrepreneur and I want to come in and I want to spin off this technology into a company, what would you say about this gripper would be attractive to a potential entrepreneur?
I think one of the most attractive properties of it is just it's pretty simple to use. I mean, it uses a form of just Raspberry Pi as the main interface. And essentially you just run a Python file in order to pull up a GUI. And then the GUI connects with the Nano VNA. And then you just start a test and you just pull the trigger in order to bring the sensors closer to the corn stalk. And it will just print out the data. Yeah. So it's very simple to use. Also, it looks like a nice little gripper mechanism, so it's very clear as to how it should be used as well.
Right. User error should be fairly low with this device. Yeah. And one of the other things that we worked into this device specifically is a GPS map overlay. So you could come in, you could select, stock 1. You could come in, take maybe 5 measurements on that stock, and you could do this throughout the day. You could do it throughout the month, and then all of that data you could overlay on a map, and then you could see from an aerial view where you're having issues, what types of issues, and then couple that with the Rodney data, which I would assume would have some sort of GPS interface as well. Yeah. I mean, again, like, it goes from stepping outside, maybe seeing if there's a storm coming and trying to make a decision based off of how you're feeling, to, oh no, I know exactly how my crop's situated. I know where I'm having issues, where things are going well. And financially, you can make those decisions about, should I harvest now, or do I have time to wait and save some money down the line?
Yeah, interesting to just add on to what you said. If you had mapped out your field, maybe over 2 years in sequence, at kind of a high level, what the farmer would probably find is that, there's spots in the field where the stock quality is reliably low.
Right.
And now that's the only spot you got to check. Unless you can, remediate, you probably only need to check that because that's your weakest link, and you harvest the field all at once. So,
right. And the time that you can save knowing that data. Right. And again, I know farmers have kind of a feel for where they have issues with their crops from time to time. But again, to have that hard data associated with it, and especially for the breeders and the growers where, if you're having issues that are due to maybe the field quality and not necessarily the stock, the corn itself or whatever it is that you're interrogating, again, that is helpful data to know. So what were some of maybe the hardest technical challenge that you had to overcome in the development of these technologies?
Now you're asking for gory details.
Maybe not too much depth, but maybe some of the things that were the most frustrating.
We use, in the Rodney, we use strain gauges. And we actually use strain gauges in a novel way, which we have a patent in on that for other purposes, where we actually have essentially a new strain gauge design, so strain gauges are often used to measure load, so load cells we call them. But we've got this new load cell, which essentially gives you both the force that's applied and the location it's applied on. So that could have potential applications in automation and robotics. Okay. But the technical challenge was, how do you take multiple strain gauges and combine all the data together so that you can reliably get the force that's applied and the location it's applied at?
Gotcha. And did you have, I would say, opportunities to improve that on both the physical side and the software side, or was one of those more challenging than the other?
They were both challenging. We're still working on the data processing side. Okay. Because there's a lot of there's several stages at which you can perform kind of data smoothing, regression, and prediction. And then there's actually a couple different ways you can calculate this. And if you calculate, the interesting thing about, all measured data has noise in it. And so even though you can calculate some of these quantities in 2 mathematical paths, one path is more sensitive to the noise than the other path. So we're playing with that to, obviously pick the better path.
Right. And I assume that's part of the ongoing research that you have going on. Okay. And James, maybe from a maybe less technical but still relevant perspective, what kind of challenges did you see in the development of the gripper that we have here?
I think that I came on into the project after all the hardware had mostly already been developed. And so when I came in, it was a lot of challenges in order to get the software running.
Right.
I think that using the Nano VNA to interface with the Raspberry Pi and then having the Python code run properly took a lot of effort.
Yeah.
The other intern who worked on it, he's very more working in software.
Mm-hmm.
And so he was spending a lot of days just curling through that code and trying to figure out where the errors were and why it wasn't working. And so, I mean, that's how coding is a lot of the time, though. It's finding the bugs and finding what's not working.
Yeah. And I was here troubleshooting with him, and I can tell you, it's very frustrating when everything is written correctly, but it just doesn't work. And then you're looking for updates or what's missing, or, did I miss a semicolon somewhere in my code? And it's very frustrating. But
James was working in my lab over the summer on the Rodney.
Fantastic.
I don't know if he mentioned that to you.
A little bit. I knew that he was working in your lab, but we hadn't talked specifically about the Rodney. So James is like our go-to resident expert in the tech transfer office on this deck. So maybe shifting gears a little bit, from an entrepreneurial perspective, maybe I'll lay out what I could see as a path to success for this technology and why someone might be interested in licensing it from BYU. So just conceptually, I'm an entrepreneur. Maybe I have a background in agriculture, right? Maybe I currently own a farm or a part of farming, or I'm, related to that industry in some way, shape, or form. And I could come in and I could essentially pick up this technology with all of those technical hurdles that you guys were talking about, overcome in some way. Obviously, there's still research that needs to be done and, developed further and developed for mass manufacturing, all those types of good things. But I could essentially take a huge leap forward into an industry that has a need, that has financial dollars associated with errors in decision making, right? That I could close that gap, and I could really put dollars and cents to farmers and say, hey, I think I could save you X number of dollars per year over the next 10 years if you integrate this technology into some of the systems that you're already using. To me, that sounds like a incredibly fantastic opportunity. And a lot of that early work of nailing the technology and figuring out how to overcome some of those, physical setup of the strain gauges, which path do we go for mathematical model in the analysis of that data? How do we package up that data, right? How do we develop this so that I can actually grip the corn stalk reliably in the right spot, right? Some of those technical challenges have already been taken care of. I don't know. What do you guys think? Does that sound crazy to you, or does that sound like a reasonable expectation for an entrepreneur?
Why the government funds basic research so that, we push the technology into the domain, the domain where the business people can pick it up and do something with it.
Yeah. And on a technology readiness level, this probably wouldn't be a pure 9 or 10, right? Because there's still some work that needs to go into it, but it's definitely not those bottom 1, 2, 3, right? I think we're more of like a 6, 7, approaching an 8 in some areas, depending on what specific aspects of the technology you're looking at.
Yeah. So I can comment on that. So we have a previous technology that's been licensed by a major company. That patent is with my former institution with New York University. That was a manual handheld device, and it's been used to perform, several 100,000 tests around the country, mostly by academic researchers.
Right.
But the seed company said it's too slow.
Right.
And so it was feedback from real, potential customers that led us to develop the Rodney, where we knew we needed to get it operating at a faster level in order to meet that market demand.
Yes. And I think ideally what you would see is this is integrated onto the tractor system with some of the data collection that's already taking place. So the operator would do literally nothing different from what they've been doing, but the owner, the farmer, right, whoever's interested, the seed company, would get this access to all of this data that they didn't have before. And again, coupled with this, right, they could go out and do those individual interrogations as necessary. And I know I've talked about that a couple times, but I really do see that as being a synergistic effect of the research that you're doing, where having that ability to spot check non-destructively, right, coupled with the overall data of the crop itself. Again, I see that as being incredibly powerful. Okay, let's see. I think those were all the main questions that I had about the technology. What other interesting aspects about this you want to talk about? I know that you ran a capstone team, I think last year here at BYU. Very briefly, for those who don't know, capstone is a what would you call it, kind of a senior project
Right.
that a lot of our engineering students take place in. I know the mechanical engineering department takes place in it. Engineering does as well. I would assume there's capstones for chemical engineering, but I'm not as connected with that department.
We typically have electrical and mechanical. Oh, I think all the students from electrical, mechanical, and then some from manufacturing, a few from chemical. We have some CS students occasionally that come over.
Right.
But I think
right.
it's growing all the time. So
Yes.
it's a great, very structured program. And so I ran two design cycles to get to the Rodney.
Okay.
One team did some early development work, came up with an idea that we eventually abandoned, and the second team was a really great team and really brought some innovative ideas, and that's how we got the Rodney.
Very nice. Yeah. And all of that development goes into the handoff of the technology into industry, right? Where you have designs and documentation, software, how we're collecting the data. All of that gets packaged up for you if you want to start to spin this off into a company. And I think this is a great fit for existing industries, but I could also see this being a startup, right? Maybe a service that you offer early on to give that data to farmers, then advance it into a device that you can then sell later on. Anyways, just thinking of different structures for how you might want to commercialize this. Very cool. Nice. And at this point, is there any really significant research that still needs to be done? I know with this device specifically, there still needs to be some data analysis research, but I feel like the Rodney really is in a good place.
The Rodney, one of the things we need to do with the Rodney is I think we've got proof of concept working pretty well. One of the things we need to figure out is how fast can we drive it through the field.
Right.
One of the things we have found is when you do the tests too quickly, you get data that's misleading.
Gotcha.
So you want to go as fast as you can on one hand,
right?
Because you want to get through. There's there's so much corn in America. You got to get through it all. But if you go too fast, so we're trying to, but that's, I think, like you said, is it a very young, immature technology, or is it more mature? By the time we get to how fast can we go, we're getting to more, a kind of refined issue.
Right. You're kind of testing the limits of the device, not the conceptual, does it actually do what we think it does?
Yep.
We know it does what we think it does, right? Now we're just, how fast can we actually go the limits of the technology in practice? Well, fantastic. Okay. Well, I think this is a great piece of tech. If you're interested, as always, reach out to the BYU Tech Transfer office. You can reach out to me directly or just generally through our website. If you have additional technical questions, we can always connect you with Dr. Cook here. He's always happy to jump on a brief call and talk over some of those technical challenges or questions that you might have if you're in the industry, questions specific to your goals with the technology. Thank you both for coming. Really appreciate it.
Having us.
Yeah, thank you.